Welcome everybody to lesson 5. And so we have officially peaked, and everything is downhill from here as of halfway through the last lesson. We started with computer vision because it's the most mature, kind of out-of-the-box, ready-to-use deep learning application. It's something which, if you're not using deep learning, you won't be getting good results. So the difference, hopefully between not doing lesson 1 versus doing lesson 1, you've gained a new capability you didn't have before, and you kind of get to see a lot of the kind of trade craft of training an effective neural net. And so then we moved into NLP because text is kind of another one which you really kind of can't do really well without deep learning, generally speaking. And it's just got to the point where it's pretty, works pretty well now. In fact, the New York Times just featured an article about the latest advances in deep learning for text yesterday, and talked quite a lot about the work that we've done in that area, along with OpenAI and Google and the Allen Institute of Artificial Intelligence. And then we've kind of finished our application journey with tabular and collaborative filtering, partly because tabular and collaborative filtering are things that you can still do pretty well without deep learning, so it's not such a big step. It's not a kind of whole new thing that you could do that you couldn't used to do. And also because we're going to try to get to a point where we understand pretty much every line of code and the implementations of these things, and the implementations of those things, it's much less intricate than vision and NLP. So as we come down this other side of the journey, which is like all the stuff we've just done, how does it actually work? By starting where we just ended, which is starting with collaborative filtering and then tabular data, we're going to be able to see what all those lines of code do by the end of today's lesson. That's our goal. So, particularly this lesson, you should not expect to come away knowing how to solve, how to do applications you couldn't do before, but instead you should have a better understanding of how we've actually been solving the applications we've seen so far. Particularly, we're going to understand a lot more about regularization, which is how we go about managing over versus underfitting. And so hopefully you can use some of the tools from this lesson to go back to your previous projects and get a little bit more performance, or handle models where previously maybe you felt like your data was not enough, or maybe you were underfitting, and so forth. And it's also going to lay the groundwork for understanding convolutional neural networks and recurrent neural networks that we'll do deep dives into in the next 2 lessons. And as we do that, we're also going to look at some new applications, some new vision and NLP applications. Let's start where we left off last week. Do you remember this picture? So this picture, we were looking at kind of what does a deep neural net look like? And we had various layers. And the first thing we pointed out is that there are only and exactly 2 types of layer. There are layers that contain parameters, and there are layers that contain activations. Parameters are the things that your model learns. They're the things that you use gradient descent to go parameters minus equals learning rate times parameters.grad. Right? That's our basic, that's what we do. Okay? And those parameters are used by multiplying them by input activations, doing a matrix product. So the yellow things are our weight matrices, or weight tensors more generally, but that's close enough. So we take some input activations or some layer activations and we multiply it by a weight matrix to get a bunch of activations. So activations are numbers, but these are numbers that are calculated. Okay, so I find in our study group I keep getting questions about where does that number come from, and I always answer it in the same way. You tell me, is it a parameter or is it an activation? Because it's one of those two things. Okay, that's where numbers come from. I guess inputs are kind of a special activation, so they're not calculated, they're just there, so maybe that's a special case. So maybe it's an input or a parameter or an activation. Activations don't only come out of matrix multiplications, they also come out of activation functions. And the most important thing to remember about an activation function is that it's an element-wise function. So it's a function that is applied to each element of the input activations in turn and creates one activation for each input element. So if it starts with a 20 long vector, it creates a 20 long vector by looking at each one of those in turn, doing one thing to it and spitting out the answer. Okay, so an element-wise function. ReLU is the main one we've looked at, and honestly, it doesn't too much matter which you pick. So we don't spend much time talking about activation functions because if you just use ReLU, you'll get a pretty good answer pretty much all the time. And so then we learnt that this combination of matrix multiplications followed by ReLUs stacked together has this amazing mathematical property called the universal approximation theorem, which is if you have big enough weight matrices and enough of them, it can solve any arbitrarily complex mathematical function to any arbitrarily high level of accuracy. Assuming that you can train the parameters, both in terms of time and data availability and so forth. Okay? So that's the bit which I find particularly more advanced computer scientists get really confused about, is they're always asking like, where's the next bit? What's the trick? How does it work? But that's it. You know, you just do those things and you pass back the gradients and you update the weights with the learning rate and that's it. So that piece where we take the loss function between the actual targets and the output of the final layer, so the final activations, we calculate the gradients with respect to all of these yellow things, and then we update those yellow things by learning rate, by subtracting learning rate times the gradient. That process of calculating those gradients and then subtracting like that is called back propagation. Okay, so when you hear the term, well, that's a very small font. So when you hear the term back propagation, it's one of these terms that neural networking folks love to use. It sounds very impressive, okay, but you can replace it with your head with weights minus equals weights.grad times learning rate, or parameters, I should say, rather than weights, a bit more general. Okay, so that's what we covered last week. And then I mentioned last week that we're going to cover a couple more things. I'm going to come back to these ones, cross entropy and softmax, later today. Let's talk about fine-tuning now. So what happens when we take a ResNet 34 and we do transfer learning? What's actually going on? So the first thing to notice is the ResNet 34 that we grab from ImageNet has a very specific weight matrix at the end. It's a weight matrix that has 1,000 columns. Why is that? Because ImageNet, the problem they ask you to solve in the ImageNet competition is please figure out which one of these 1,000 image categories this picture is. So that's why they need 1,000 things here, because in ImageNet, this target vector is length 1,000. It's you've got to pick the probability that it's which one of those 1,000 things. So there's a couple of reasons this weight matrix is no good to you when you're doing transfer learning. The first is that you probably don't have 1,000 categories. You know, I was trying to do teddy bears, black bears, or brown bears, so I don't want 1,000 categories. And the second is even if I did have exactly 1,000 categories, they're not the same 1,000 categories that are in ImageNet. So basically, this whole weight matrix is a waste of time for me. So what do? We throw it away. So when you go create CNN in FastAI, it deletes that. And what does it do instead? Instead, it puts in 2 new weight matrices in there for you, with a ReLU in between. And so there are some defaults as to what size this first one is, but the second one, the size there is as big as you need it to be. So in your data bunch, which you pass to your learner, from that we know how many activations you need. If you're doing classification, it's however many classes you have. If you're doing regression, it's however many numbers you're trying to predict in the regression problem. And so remember that if your data bunch is called data, that'll be called data.c. So we'll add for you this weight matrix of size data.c by however much was in the previous layer. Okay, so now we need to train those because initially these weight matrices are full of random numbers. Okay? Because new weight matrices are always full of random numbers if they're new, and these ones are new. We've grabbed them and thrown them in there. So we need to train them. But the other layers are not new. The other layers are good at something, right? And what are they good at? Well, let's remember that Zeiler and Fergus paper. Here are examples of some visualization of some filters, some weight matrices in the first layer, and some examples of some things that they found. Right? So the first layer had one part of the weight matrix was good at finding diagonal edges in this direction. And then in layer 2, one of the filters was good at finding corners in the top left. And then in layer 3, one of the filters was good at finding repeating patterns. Another one was good at finding round orange things. Another one was good at finding kind of like furry or floral textures. So as we go up, they're becoming more sophisticated, but also more specific, right? So like layer 4, I think, was finding like eyeballs, for instance. Now, if you're wanting to transfer learn to something for histopathology slides, there's probably going to be no eyeballs in that, right? So the later layers are no good for you. But there'll certainly be some repeating patterns, and there'll certainly be some diagonal edges, right? So the earlier you go in the model, the more likely it is that you want those weights to stay as they are. Well, to start with, we definitely need to train these new weights because they're random. So let's not bother training any of the other weights at all to start with. So what we do is we basically say, let's freeze. Let's freeze all of those other layers. So what does that mean? All it means is that we're asking FastAI and PyTorch that when we train, however many epochs we do, when we call fit, don't backpropagate the weights. Don't backpropagate the gradients back into those layers. In other words, when you go parameters equals parameters minus learning rate times gradient, only do it for the new layers, don't bother doing it for the other layers. That's what freezing means, okay? Just means don't update those parameters. So it'll be a little bit faster as well, because there's a few less calculations to do. It'll take up a little bit less memory because there's a few less gradients that we have to store. But most importantly, it's not going to change weights that are already better than nothing. They're better than random, at the very least. So that's what happens when you call freeze. It doesn't freeze the whole thing. It freezes everything except the randomly generated added layers that we put on for you. So then what happens next? Okay, after a while, we say, okay, this is looking pretty good. We probably should train the rest of the network now. So we unfreeze, right? And so now we're going to train the whole thing, but we still have a pretty good sense that these new layers we added to the end probably need more training, and these ones right at the start that might just be like diagonal edges probably don't need much training at all. So we split our model into a few sections, right? And we say, let's give different parts of the model different learning rates. So this part of the model, we might give a learning rate of 1e neg 5. And this part of the model, we might give a learning rate of 1e neg 3, say. And so what's going to happen now is that we can keep training the entire network, but because the learning rate for the early layers is smaller, it's going to move them around less, because we think they're already pretty good. And also, like, if it's already pretty good to the optimal value, if you used a higher learning rate, it could kick it out, right? It could actually make it worse, which we really don't want to happen. Okay, so this process is called using discriminative learning rates. You won't find much online about it, because I think we were kind of the first to use it for this purpose, or at least talk about it extensively. Maybe probably other people used it without writing it down. So most of the stuff you'll find about this will be FastAI students. But it's starting to get more well-known slowly now. But it's a really, really important concept. For transfer learning, without using this, you just can't get nearly as good results. So how do we do discriminative learning rates in FastAI? Anywhere you can put a learning rate in FastAI, such as with the fit function, the first thing you put in is the number of epochs, and then the second thing you put in is learning rate. Same if you use fit one cycle. The learning rate, you can put a number of things there. You can put a single number, like 1e neg 3. You can write a slice, so you can write slice, for example, 1e neg 3, with a single number, or you can write slice with two numbers. What do each of those mean? In the first case, just using a single number means every layer gets the same learning rate. So you're not using discriminative learning rates. If you pass a single number to slice, it means the final layers get a learning rate of whatever you wrote down, 1e neg 3. And then all the other layers get the same learning rate, which is that divided by 3. Okay, so all of the other layers will be 1e neg 3 divided by 3. The last layers will be 1e neg 3. And in the last case, the final layers, these randomly added layers, will still be, again, 1e neg 3. The first layers will get 1e neg 5, and the other layers will get learning rates that are equally spread between those two, so multiplicatively equal, right? So if there were 3 layers, there would be 1e neg 5, 1e neg 4, 1e neg 3. So equal multiples each time. One slight tweak, to make things a little bit simpler to manage, we don't actually give a different learning rate to every layer. We give a different learning rate to every layer group, which is just we decide to put the groups together for you. And so specifically what we do is the randomly added extra layers, we call those one layer group. This is by default, you can modify it. And then all the rest, we split in half into 2 layer groups. So by default, at least with a CNN, you'll get 3 layer groups. And so if you say slice 1e neg 5, 1e neg 3, you will get 1e neg 5 learning rate for the first layer group, 1e neg 4 for the second, 1e neg 3 for the third. So now if you go back and look at the way that we're training, hopefully you'll see that this makes a lot of sense. This divided by 3 thing is a little weird, and we won't talk about why that is until part 2 of the course. It's a specific quirk around batch normalization. So we can discuss that in the advanced topic if anybody's interested. All right, so that is fine-tuning. So hopefully that makes that a little bit less mysterious. So we were looking at collaborative filtering last week. And in the collaborative filtering example, we called fit1cycle and we passed in just a single number. And that makes sense because in collaborative filtering, we only have one layer. There's a few different pieces in it, but there isn't, you know, a matrix multiply followed by an activation function followed by another matrix multiply. I'm going to introduce another piece of jargon here. They're not always exactly matrix multiplications. There's something very similar. They're linear functions that we add together. But the more general term for these things that are a bit more general than matrix multiplications is affine functions. Okay, so if you hear me say the word affine function, you can replace it in your head with matrix multiplication. But as we'll see when we do convolutions, convolutions are matrix multiplications where some of the weights are tied, and so it would be slightly more accurate to call them affine functions. And I like to introduce a little bit more jargon each lesson so that when you read books or papers or watch other courses or read documentation, there will be more of the words that you'll recognize. Okay? So when you see affine function, it just means a linear function, right? And it means something very, very close to matrix multiplication. A matrix multiplication is the most common kind of affine function, at least in deep learning. Specifically for collaborative filtering, the model we were using was this one. It was where we had a bunch of numbers here and a bunch of numbers here, and we took the dot product of them. And given that one here is a row and one is a column, we can actually, that's the same as a matrix product. So M mult in Excel multiplies matrices, so here is the matrix product of those two. And so I started this training last week by using Solver in Excel, and we never actually went back to see how it went, so let's go and have a look now. So the average sum of squared error got down to 0.39. So we're trying to predict something on a scale of 0.5 to 5. So on average, we're being wrong by about 0.4. That's pretty good. And you can kind of see it's pretty good if you look at like 351 is what it meant to be, 3.25, 5.1, 0.98. It's pretty close, right? So you get the general idea. And then I started to talk about this idea of embedding matrices. And so in order to understand that, let's put this worksheet aside and look at another worksheet. So here's another worksheet. And what I've done here is I have copied over those two weight matrices from the previous worksheet, right? Here's the one for users, and here's the one for movies. And the movies one, I've transposed it, so it's now got exactly the same dimensions as the users one. Okay? So here are two weight matrices. Initially they were random. We can train them with gradient descent. In the original data, the user IDs and movie IDs were numbers like these. Okay? To make life more convenient, I've converted them to numbers from 1 to 15. Okay? So in these columns, I've got, for every rating, I've got user ID, movie ID, rating, using these mapped numbers so that they're contiguous starting at 1. Okay. Now I'm going to replace user ID number 1 with this vector. The vector contains a 1 followed by 14 zeros. And then user number 2, I'm going to replace with a vector of 0, and then 1, and then 13 zeros, and so forth. So movie ID 14, all these are movie ID 14, I've also replaced with another vector, which is 13 zeros, and then a 1, and then a 0. Okay. So these are called one-hot encodings, by the way. So this is not part of a neural net. This is just like some input pre-processing where I'm literally making this my new inputs. This is my new inputs for my movies. This is my new inputs for my users. Okay, so these are the inputs to a neural net. So what I'm going to do now is I'm going to take this input matrix and I'm going to do a matrix multiply by this weight matrix. And that'll work because this has 15 rows and this has 15 columns. So I can multiply those two matrices together because they match. And you can do matrix multiplication in Excel using the mmult function. Just be careful if you're using Excel, because this is a function that returns multiple numbers. You can't just hit enter when you finish with it, you have to hit Control-Shift-Enter. Control-Shift-Enter means this is an array function, it's something that returns multiple values. So here is the matrix product of this input matrix of inputs and this parameter matrix or weight matrix. So that's just a normal neural network layer. Okay? It's just a regular matrix multiply. And so we can do the same thing for movies. And so here's the matrix multiply for movies. Well, here's the thing. This input we claim is this kind of one-hot encoded version of user ID number 1. And these activations are the activations for user ID number 1. Why is that? Because if you think about it, a matrix multiplication between a one-hot encoded vector and some matrix is actually going to find the nth row of that matrix when the 1 is in position n. Does that make sense? So what we've done here is we've actually got a matrix multiply that is creating these output activations, right? But it's doing it in a very interesting way, which is it's effectively finding a particular row in the input matrix. So having done that, we can then multiply those two sets together, just a dot product, and we can then find the loss squared, and then we can find the average loss, and lo and behold, that number, 0.39, is the same as this number, because they're doing the same thing. So this one was kind of finding this particular user's embedding vector. This one is just doing a matrix multiply, and therefore we know they are mathematically identical. So let's lay that out again. So here's our final version. This is the same weight matrices again, exactly the same, I've copied them over. And here's those user IDs and movie IDs again, right? But this time I've laid them out just in a normal kind of tabular form, just like you would expect to see in the input to your model. And this time, I've got exactly the same set of activations here that I had here. But in this case, I've calculated these activations using Excel's offset function, which is an array lookup, right? It says, find the first row of this. So this is doing it as an array lookup. So this version is identical to this version, but obviously it's much less memory intensive and much faster, because I don't actually create the one-hot encoded matrix, and I don't actually do a matrix multiply, because that matrix multiply is nearly all multiplying by 0, which is a total waste of time. So in other words, multiplying by a one-hot encoded matrix is identical to doing an array lookup. Therefore, we should always do the array lookup version. And therefore, we have a specific way of saying, I want to do a matrix multiplication by a one-hot encoded matrix without ever actually creating it. I'm just instead going to pass in a bunch of ints and pretend they're one-hot encoded. And that is called an embedding, right? So you might have heard this word embedding all over the place as if it's some magic advanced mathy thing. But embedding means look something up in an array. Okay? But it's interesting to note that looking something up in an array is mathematically identical to doing a matrix product by a one-hot encoded matrix, and therefore an embedding fits very nicely in our standard model of how neural networks work. So now, suddenly, it's as if we have another whole kind of layer. It's a kind of layer where we get to look things up in an array. But we actually didn't do anything special, right? We just added this computational shortcut, this thing called an embedding, which is simply a fast and memory-efficient way of multiplying by a one-hot encoded matrix. Okay, so this is really important, because when you hear people say embedding, you need to replace it in your head with an array lookup, which we know is mathematically identical to a matrix multiplied by a one-hot encoded matrix. Here's the thing though, it has kind of interesting semantics, right? Because when you do multiply something by a one-hot encoded matrix, you get this nice feature where the rows of your weight matrix, the values only appear for row number 1, for example, where you get user ID number 1 in your inputs, right? So in other words, you kind of end up with this weight matrix where certain rows of weights correspond to certain values of your input. And that's pretty interesting. It's particularly interesting here because, going back to a kind of most convenient way to look at this, because the only way that we can calculate an output activation is by doing a dot product of these two input vectors, that means that they kind of have to correspond with each other, right? Like there has to be some way of saying if this number for a user is high and this number for a movie is high, then the user will like the movie. So the only way that can possibly make sense is if these numbers represent features of personal taste and corresponding features of movies. For example, the movie has John Travolta in it, and user ID likes John Travolta, then you'll like this movie. Okay? So like, we're not actually deciding the rows mean anything. We're not doing anything to make the rows mean anything. But the only way that this gradient descent could possibly come up with a good answer is if it figures out what the aspects of movie taste are and the corresponding features of movies are. So those underlying kind of features that appear are called latent factors, or latent features. They're these hidden things that were there all along, and once we train this neural net, they suddenly appear. Right? Now here's the problem. No one's going to like Battlefield Earth, right? It's not a good movie, even though it has John Travolta in it. So how are we going to deal with that, right? Because there's this feature called I like John Travolta movies, and this feature called this movie has John Travolta, and so this is now like, you're going to like the movie, but we need to have some way to say, unless it's Battlefield Earth, or you're a Scientologist, either one, right? So how do we do that? We need to add in bias, right? So here is the same thing again. Same weight matrix, sorry, not the same weight matrix, it's the same construct, right? Same shape of everything. But this time we've got an extra row. So now, this is not just the matrix product of that and that, but I'm also adding on this number and this number, which means now each movie can have an overall, this is a great movie versus this isn't a great movie. And every user can have an overall, this user rates movies highly or this user doesn't rate movies highly. So that's called the bias. So this is hopefully going to look very familiar, right? This is the same usual linear model concept or linear layer concept from a neural net, that you have a matrix product and a bias. And do you remember from lesson 2, the lesson 2 SGD notebook, you never actually need a bias. You could always just add a column of 1s to your input data, and then that gives you bias for free. But that's pretty inefficient, right? So in practice, all neural networks library explicitly have a concept of bias. We don't actually add the column of ones. So what does that do? Well, just before I came in today, I ran tools solver, or now it's data solver, on this as well. And we can check the RMSE. And so the root mean squared here is 0.32 versus the version without bias was 0.39. Okay, so you can see that this slightly better model gives us a better result. And it's better because it's giving both more flexibility, right? And it's also just makes sense semantically that you need to be able to say, it's not whether I like the movie is not just about the combination of what actors it has and whether it's dialogue driven and how much action is in it, but just, is it a good movie? Okay, or am I somebody who rates movies highly? Okay, so there's all the pieces of this collaborative filtering model. How are we going, Francisco? Any questions? We have 3 questions. Okay. Okay. So our first question then is, when we load a pre-trained model, can we explore the activation grids to see what they might be good at recognizing? Yes, you can. And we will learn how to, should be in the next lesson. Can we have an explanation of what the first argument in fit one cycle actually represents? Is it equivalent to an epoch? Yes. The first argument to fit one cycle, or fit, is number of epochs. It's, in other words, an epoch is looking at every input once. So if you do 10 epochs, you're looking at every input 10 times. And so there's a chance you might start overfitting if you've got lots and lots of parameters and a high learning rate. If you only do 1 epoch, it's impossible to overfit. So that's why it's kind of useful to remember how many epochs you're doing. Can we have an explanation? Did that one? What is an affine function? An affine function is a linear function. I don't know if we need much more detail than that. If you're multiplying things together and adding them up, it's an affine function. I'm not going to bother with the exact mathematical definition, partly because I'm a terrible mathematician and partly because it doesn't matter. But if you just remember that you're multiplying things together and then adding them up, that's the most important thing. It's linear. Okay? And therefore, if you put an affine function on top of an affine function, that's just another affine function. You haven't won anything at all. That's a total waste of time, right? So you need to sandwich it with any kind of nonlinearity, pretty much works, right? Including replacing the negatives with zeros, which we call ReLU. Okay, so if you do affine, ReLU, affine, ReLU, affine, ReLU, you have a deep neural network. Okay, so let's go back to the collaborative filtering notebook. And this time we're going to grab the whole MovieLens 100K data set. There's also a 20 million data set, by the way. So really great project available, made by this group called GroupLens. They actually update the MovieLens data sets on a regular basis, but they helpfully provide the original one. And we're going to use the original one because that means that we can compare to baselines. Because everybody, basically they say, hey, if you're going to compare to baselines, make sure you all use the same data set. Here's the one you should use. Unfortunately, it means that we're going to be restricted to movies that are before 1998. So maybe you won't have seen them all, but that's the price we pay. You can replace this with ML Latest when you download it and use it if you want to play around with movies that are up to date. Okay, the original MovieLens dataset, the more recent ones are in a CSV file that's super convenient to use. The original one is a slightly messy. First of all, they don't use commas for delimiters, they use tabs. So in pandas, you can just say what's the delimiter when you load it in. The second is they don't add a header row so that you know what column is what. So you have to tell pandas there's no header row. And then since there's no header row, you have to tell pandas what are the names of the columns. Other than that, that's all we need. Okay, so we can then have a look at head, which remembers the first few rows, and there is our user ratings, user movie rating. And let's make it more fun. Let's see what the movies actually are. I'll just point something out here, which is there's this thing called encoding equals. I'm going to get rid of it. And I get this error, Unicode. I just want to point this out because you'll all see this at some point in your lives. Codec can't decode, blah, blah, blah. What this means is that this is not a Unicode file. This will be quite common when you're using data sets that are a little bit older. Back before, us folks in the West really realized that there are people that use languages other than, well, English people, languages other than English. Nowadays, we're much better at handling different languages. We use this standard called Unicode for it, and Python very helpfully uses Unicode by default. But so if you try to load an old file that's not Unicode, you actually, believe it or not, have to guess how it was coded. But since it's really likely that it was created by, some Western European or American person, they almost certainly used Latin 1. So if you just pop in encoding equals Latin 1, if you use file open in Python or pandas open or whatever, that will generally get around your problem. Again, they didn't have the names, so we had to list what the names are. This is kind of interesting. They had a separate column for every one of however many genres they had, 19 genres. And you'll see this looks one hot encoded, but it's actually not. It's actually n hot encoded. In other words, a movie can be in multiple genres. We're not going to look at genres today, but it's just interesting to point out that this is a way that sometimes people will represent something like genre. In the more recent version, they actually list the genres directly, which is much more convenient. Okay, so I find life is, so we've got 100,000 ratings. I find life is easier when you're modeling, when you actually denormalize the data. So I actually want the movie title directly in my ratings. So Pandas has a merge function to let us do that. So here's the ratings table with actual titles. So as per usual, we can create a data bunch for our application, so a Colab data bunch for the Colab application from what? From a data frame. There's our data frame. Set aside some validation data. Really, we should use the validation sets and cross-validation approach that they used if you're going to properly compare with a benchmark. So take these comparisons with a grain of salt. By default, Colab Data Bunch assumes that your first column is user, second column is item, third column is rating. But now we're actually going to use the title column as item, so we have to tell it what the item column name is. And then all of our data bunches support show batch, so you can just check what's in there, and there it is. Okay. So I'm going to try and get as good a result as I can. So I'm going to try and use whatever tricks I can come up with to get a good answer. Now, one of the tricks is to use the Y range. And remember, the Y range was the thing that made the final activation function a sigmoid. And specifically, last week we said, let's have a sigmoid that goes from 0 to 5. And that way it's going to ensure that it's going to help the neural network predict things that are in the right range. I actually didn't do that in my Excel version. And so you can see I've actually got some negatives, right? And there's also some things bigger than 5. So if you want to beat me in Excel, you could add the sigmoid to Excel and train this, and you'll get a slightly better answer. Now, the problem is that a sigmoid actually asymptotes at, say, whatever the maximum is. We said 5, right? Which means you can never actually predict 5. But plenty of movies have a rating of 5, so that's a problem. So actually, it's slightly better to make your Y range go from a little bit less than the minimum to a little bit more than the maximum. And the minimum of this data is 0.5, and the maximum is 5. So this range is just a little bit further. So that's one little trick to get a little bit more accuracy. The other trick I used is to add something called weight decay, and we're going to look at that next, okay, after this section. We're going to learn about weight decay. So then, how many factors do you want? Well, what are factors? The number of factors is the width of the embedding matrix. So why don't we say embedding size? Maybe we should, but in the world of collaborative filtering, they don't use that word. They use the word factors because of this idea of latent factors. And because the standard way of doing collaborative filtering has been with something called matrix factorization. And in fact, what we just saw happens to actually be a way of doing matrix factorization. So we've actually accidentally learnt how to do matrix factorization today. So this is a term that's kind of specific to this domain, okay? But you can just remember it as the width of the embedding matrix. And so why 40? Well, this is one of these architectural decisions you have to play around with and see what works. So I tried 10, 20, 40, and 80, and I found 40 seemed to work pretty well. And it trained really quickly. So like you can chuck it in a little for loop to try a few things and see what looks best. And then for learning rates, I use the learning rate finder as usual. 5e neg 3 seemed to work pretty well. Remember, this is just a rule of thumb, right? 5e neg 3 is a bit lower than both Sylvain's rule and my rule. So Sylvain's rule is find the bottom and go back by 10. So his rule would be more like 2e neg 2, I reckon. My rule is kind of find about the steepest section, which is about here, which again, like often it agrees with Sylvain, so that would be about 2e neg 2. I tried that, and I always like to try like 10x less and 10x more, just to check, and actually I found a bit less was helpful. So the answer to the question like, should I do blah, is always try blah and see. Now that's how you actually become a good practitioner. So that gave me 0.813, right? And as usual, you can save the result to save you another 33 seconds from having to do it again later. And so there's a library called LibRec, and they publish some benchmarks for movie lens 100K, and there's a root mean squared error section, and about 0.91 is about as good as they seem to have been able to get. 0.91 is the root mean squared error. We use the mean squared error, not the root. So we have to go 0.91 squared, which is 0.83, and we're getting 0.81. So that's cool. With this very simple model, we're doing a little bit better. Quite a lot better, actually. Although, as I said, take it with a grain of salt because we're not doing the same splits and the same cross-validation. So we're at least highly competitive with their approaches. Okay, so we're going to look at the Python code that does this in a moment. But for now, just take my word for it that we're going to see something that's just doing this, right? Looking things up in an array and then multiplying them together, adding them up, and doing the mean squared error loss function. So given that, and given that we noticed that the only way that that can do anything interesting is by trying to kind of find these latent factors, it makes sense to look and see what they found, right? Particularly since, as well as finding latent factors, we also now have a specific bias number for every user and every movie, right? Now, you could just say, what's the average rating for each movie? But there's a few issues with that. In particular, this is something you see a lot with like anime. People who like anime just love anime, right? And so they watch lots of anime and then they just rate all the anime highly. And so very often on kind of charts of movies, you'll see a lot of anime at the top, right? Particularly if it's like, 100 long series of anime, you'll find, every single item of that series in the top 1,000 movie list or something. So how do we deal with that? Well, the nice thing is that instead, if we look at the movie bias, right, the movie bias says kind of, once we've included the user bias, right, which for an anime lover might be a very high number because they're just rating a lot of movies highly. And once we account for the specifics of this kind of movie, which again might be people love anime, right? What's left over is something specific to that movie itself. So it's kind of interesting to look at movie bias numbers as a way of saying what are the best movies, or what do people really like as movies, even if those people don't rate movies very highly, or even if that movie doesn't have the kind of features that people tend to have rate highly. So you get this kind of nice, it's funny to say this, by using the bias, we get an unbiased kind of movie score. So how do we do that? Well, to make it interesting, particularly because this data set only goes to 1998, let's only look at movies that plenty of people watch, right? So we'll use pandas to grab our rating movie table, group it by title, and then count the number of ratings. And not measuring how high they're rating, just how many ratings do they have, okay? And so the top 1,000 are the movies that have been rated the most, and so they're hopefully movies that we might have seen. Okay, that's the only reason I'm doing this. And so I've called this top movies, by which I mean not good movies, just movies we're likely to have seen. So not surprisingly, Star Wars is the one that at that point the most people had put a rating to. Independence Day. There you go. So we can then take our learner that we trained and ask it for the bias of the items listed here. Okay, so is item equals true, you would pass true to say I want the items, or false to say I want the users. So this is kind of like a pretty common piece of nomenclature for collaborative filtering. These IDs tend to be called users. These IDs tend to be called items. Even if your problem has got nothing to do with users and items at all, we just use these names for convenience, okay? So they're just words. So in our case, we want the items. This is the list of items we want. We want the bias. So this is specific to collaborative filtering. And so that's going to give us back 1,000 numbers, right? Because we asked for, this has 1,000 movies in it. So we can now take, and just for comparison, let's also group the titles by the mean rating. So then we can zip through, so going through together, each of the movies along with the bias, and grab their rating and the bias and the movie, and then we can sort them all by the zero index thing, which is the bias. So here are the lowest numbers. So I can say, Mortal Kombat Annihilation, not a great movie. Lawnmower Man 2, not a great movie. I haven't seen Children of the Corn, but we did have a long discussion at SF Study Group today, and people who have seen it agree, not a great movie. And you can kind of see, some of them actually have pretty decent ratings, even though, relative to, right? So this one's actually got a much higher rating than the next one, right? But, that's kind of saying, well, the kind of actors that were in this and the kind of movie that this was and the kind of people who like it, who watch it, you would expect it to be higher. And then here's the sort by reverse, okay? Schindler's List, Titanic, Shawshank Redemption, seems reasonable. And again, you can kind of look for ones where the rating, isn't that high, but it's still very high here. So that's kind of at least in 1998, people weren't that into Leonardo DiCaprio, or, people aren't that into dialogue-driven movies, or people aren't that into romances or whatever, but still people liked it more than you would have expected. So it's interesting to kind of interpret our models in this way. We can go a bit further and grab not just the biases, but the weights. So that is these things. And again, we're going to grab the weights for the items for our top movies. And that is 1000 by 40 because we asked for 40 factors. So rather than having a width of 5, we have a width of 40. Often, really there isn't really conceptually 40 latent factors involved in taste, and so trying to look at the 40 can be, not that intuitive. So what we want to do is we want to squish those 40 down to just 3. And there's something that we're not going to look into called PCA, stands for Principal Components Analysis. So this is movie W is a torch tensor, and FastAI adds the PCA method to torch tensors. And what PCA does, Principal Components Analysis, is it's a simple linear transformation that takes an input matrix and tries to find a smaller number of columns that kind of cover a lot of the space of that original matrix. If that sounds interesting, which it totally is, you should check out our course Computational Linear Algebra, which Rachel teaches, where we will show you how to calculate PCA from scratch and why you'd want to do it and lots of stuff like that. It is absolutely not a prerequisite for anything in this course, but it's definitely worth knowing that taking layers of neural nets and chucking them through PCA is very often a good idea. Because very often you have like way more activations than you want in a layer, and there's all kinds of reasons you might want to play with it. For example, Francisco, who's sitting next to me today, has been working on something to do image similarity, right? And for image similarity, a nice way to do that is to compare activations from a model, but often those activations will be huge, and therefore your thing could be really slow and unwieldy. So people often, for something like image similarity, will chuck it through a PCA first, and that's kind of cool. In our case, we're just going to do it so that we take our 40 components down to 3 components, so hopefully they'll be easier for us to interpret. So we can grab each of those 3 factors. We'll call them factor 0, 1, and 2. Let's grab that movie components and then sort. And now the thing is, we have no idea what this is going to mean, but we're pretty sure it's going to be some aspect of taste and movie feature. So if we print it out, the top and the bottom, we can see that the highest ranked things on this feature, you would kind of describe them as, connoisseurs movies, I guess. Like Chinatown, really classic Jack Nicholson movie. Everybody knows Casablanca. And even like Wrong Trousers is like this kind of classic claymation movie and so forth, right? So yeah, this is definitely measuring like things that are very high on the kind of connoisseur level, whereas maybe Home Alone 3, not such a favorite with connoisseurs, perhaps. Which is not to say that there aren't people who don't like it, right? But probably not the same kind of people that would appreciate Secrets and Lies. Okay, so you can kind of see this idea that this has found some feature of movies and a corresponding feature of the kind of things people like. So let's look at another feature. So here's factor number 1. So this seems to have found like, okay, these are just big hits that you could watch with the family, These are definitely not that, Trainspotting, very gritty kind of, thing. So again, it's kind of found this interesting feature of taste, and we could even like draw them on a graph, right? I've just colored them randomly to make them easier to see, and you can kind of see like, and this is just the top 50 most popular movies by rating, by how many times they've been rated. And so kind of on this one factor, you've got the head of the Terminators really high up here, and the kind of English Patient and Schindler's List at the other end, and then kind of here's your Godfather and Monty Python over here, and Independence Day and Liar Liar over there. So you get the idea. So it's kind of fun. It would be interesting to see if you can come up with some stuff at work or other kind of data sets where you could try to pull out some features and play with them. So how does that work? Any questions? One. Okay. The question is, why am I sometimes getting negative loss when training? You shouldn't be. So you're doing something wrong. So show us your I mean, particularly since people are upvoting this, I guess other people have seen it too. So put it on the forum. I mean, they said they're doing negative log likelihood. Yeah, so we're going to be learning about cross entropy and negative log likelihood after the break today. They are loss functions that have very specific expectations about what your input looks like, and if your input doesn't look like that, then they're going to give very weird answers. So probably you pressed the wrong buttons, so don't do that. Okay, so we said Colab learner. And so here is the Colab learner function. The Colab learner function, as per usual, takes a data bunch. And normally learners also take something where you ask for a particular architectural details. In this case, there's only one thing which does that, which is basically, do you want to use a multi-layer neural net, or do you want to use a classic collaborative filtering? And we're only going to look at the classic collaborative filtering today, or maybe we'll briefly look at the other one too. We'll see. And so what actually happens here? Well, basically, we're going to we create an embedding dot bias model, and then we pass back a learner which has our data and that model. So obviously all the interesting stuff is happening here in embedding.bias. So let's take a look at that. I clearly pressed the wrong button. Embedding.bias. There we go. Okay, so here's our embedding.bias model. It is a nn.module. So in PyTorch, to remind you, all PyTorch layers and models are nn.modules. They are things that, once you create them, look exactly like a function. You call them with parentheses and you pass them arguments. But they're not functions. They don't even have, normally in Python, to make something look like a function, you have to give it a method called dunder call. Remember, that means underscore, underscore, call, underscore, underscore, which doesn't exist here. And the reason is that PyTorch actually expects you to have something called forward. And that's what PyTorch will call for you when you call it like a function. So when this model is being trained to get the predictions, it's actually going to call forward for us. So this is where we do the calculations, right? To calculate our predictions. So this is where you can see we grab our, why is this users rather than user? Well, that's because everything's done a mini batch at a time, right? So it's kind of, when I read the forward in a PyTorch module, I tend to ignore in my head the fact that there's a mini batch, and I pretend there's just one. Because PyTorch automatically handles all of the stuff about doing it to everything in the mini batch for you, right? So let's pretend there's just one user, right? So grab that user and what is this? Self.u_weight. Self.u_weight is an embedding. We create an embedding for each of users by factors, items by factors, users by one, items by one. Well, that makes sense, right? So users by one is here. That's the user's bias, right? And then users by factor is here. So users by factors is the first tuple, so that's going to go in u_weight. And users, comma, one is the third, so that's going to go in u_bias. So remember, when PyTorch creates our nn.module, it calls dunder init. And so this is where we have to create our weight matrices, right? And we don't normally create the actual weight matrix tensors. We normally use PyTorch's convenience functions to do that for us. And we're going to see some of that after the break. So for now, just recognize that this function is going to create an embedding matrix for us. It's going to be a PyTorch nn.module as well. So therefore, to actually pass stuff into that embedding matrix and get activations out, you treat it as if it was a function, okay? Stick it in parentheses. So if you want to look in the PyTorch source code and find nn.embedding, you will find there's something called .forward in there, which will do this array lookup for us. So here's where we grab the users. Here's where we grab the items. And so we've now got the embeddings for each, right? And so at this point, we're kind of like here, and we found that and that. So we multiply them together and sum them up, and then we add on the user bias and the item bias. And then if we've got a Y range, then we do our sigmoid trick. And so the nice thing is, you now understand the entirety of this model. And this is not just any model, this is a model that we just found is at the very least highly competitive with, and perhaps slightly better than, some published table of pretty good numbers from a software group that does nothing but this. So you're doing well, right? This is nice. So that's probably a good place to have a break. And so after the break, we're going to come back and we're going to talk about the one piece of this puzzle we haven't learnt yet, which is what the hell does this do? Okay, so let's come back at 7:50. Okay, so this idea of interpreting embeddings is really interesting, and as we'll see later in this lesson, the things that we create for categorical variables more generally in tabular data sets are also embedding matrices. And again, that's just a normal matrix multiply by a one-hot encoded input, where we skip the computational and memory burden of it by doing it in a more efficient way. And it happens to end up with these interesting semantics kind of accidentally. And there was this really interesting paper by these folks who came second in a Kaggle competition for something called Rossmann. We'll probably look in more detail at the Rossmann competition in part 2. I think we're going to run out of time in part 1, but it's basically this pretty standard tabular stuff. The main interesting stuff is in the pre-processing. And it was interesting because they came second, despite the fact that the person who came first and pretty much everybody else towards the top of the leaderboard did a massive amount of highly specific feature engineering, whereas these folks did way less feature engineering than anybody else. But instead they used a neural net, and this was at a time in 2016 when just no one did that. No one was doing neural nets for tabular data. So they have, you know, the kind of stuff that we've been talking about kind of arose there, or at least was kind of popularized there. And when I say popularized, I mean only popularized a tiny bit. Still, most people aren't aware of this idea. But it's pretty cool because in their paper, they showed that the mean average percentage error for various techniques, k-nearest neighbors, random forest, and gradient boosted trees, well, first, you know, neural nets just worked a lot better, but then with entity embeddings, which is what they call this, just using entity matrices in tabular data, they actually added the entity embeddings to all of these different tasks after training them, and they all got way better, right? So neural nets with entity embeddings are still the best, but a random forest with entity embeddings was not at all far behind, and you know that's often kind of nice, right? Because you could train these entity matrices for products or stores or genome motifs or whatever, and then use them in lots of different models, possibly, you know, using faster things like random forests, but getting a lot of the benefits. But here was something interesting. They took a two-dimensional projection of their embedding matrix for state, for example, German state, because this was a German supermarket chain, I think, using the same kind of approach we did. I don't remember if they used PCA or something else slightly different. And then here's the interesting thing. I've circled here, a few things in this embedding space, and I've circled it with the same color over here. And here I've circled some, same color over here, and it's like, oh my God, the embedding projection has actually discovered geography. Like they didn't do that, right? But it's found things that are nearby each other in grocery purchasing patterns, because this was about predicting how many sales there will be. There is some geographic element of that. In fact, here is a graph of the distance between two embedding vectors. So you can just take an embedding vector and say, what's the sum of squared, compared to some other embedding vector, and that's the Euclidean distance. What's the distance in embedding space? And then plot it against the distance in real life between shops, and you get this very strong positive correlation. Here is an embedding space for the days of the week, and as you can see, there's a very clear path through them. Here's the embedding space for the month of the year. And again, there's a very clear path through them. So embeddings are amazing. And I don't feel like anybody's even close to exploring the kind of interpretation that you could get, right? So if you've got genome motifs or plant species or products that your shop sells or whatever, it would be really interesting to train a few models and try and kind of fine-tune some embeddings and then start looking at them in these ways in terms of similarity to other ones and clustering them and projecting them into 2D spaces and whatever. I think it's really interesting. So we were trying to make sure we understood what every line of code did in this pretty good Colab learner model we built. And so the one piece missing is this WD piece. And WD stands for weight decay. So what is weight decay? Weight decay is a type of regularization. What is regularization? Well, let's start by going back to this nice little chart that Andrew Ng did in his terrific machine learning course, where he plotted some data and then showed a few different lines through it. This one here, because Andrew's at Stanford, he has to use Greek letters. Okay, so we can say this is A plus BX, but if you want to go there, theta naught plus theta 1x is a line, right? It's a line even if it's got Greek letters, it's still a line. So here's a second degree polynomial, A plus BX plus CX squared, bit of curve, right? And here's a high degree polynomial, which is curvy as anything. So models with more parameters tend to look more like this. And so in traditional statistics, we say, hey, let's use less parameters because we don't want it to look like this. Because if it looks like this, then the predictions over here and over here, they're going to be all wrong, right? It's not going to generalize well. We're overfitting. So we avoid overfitting by using less parameters. And so if any of you are unlucky enough to have been brainwashed by a background in statistics or psychology or econometrics or any of these kinds of courses, you're going to have to unlearn the idea that you need less parameters. Because what you instead need to realize this is you were fed this lie that you need less parameters because it's a convenient fiction for the real truth, which is you don't want your function to be too complex. And having less parameters is one way of making it less complex. But what if you had 1,000 parameters and 999 of those parameters were 1e neg 9? Well, what if there was 0? If they're 0, they're not really there. Or if they're 1e neg 9, they're hardly there, right? So why can't I have lots of parameters? if like lots of them are really small? And the answer is you can. Okay, you know, so this thing of like counting the number of parameters is how we limit complexity is actually extremely limiting. It's a fiction that really has a lot of problems, right? And so if in your head complexity is scored by how many parameters you have, you're doing it all wrong, right? Score it properly, right? So why do we care? Why would I want to use more parameters? Because more parameters means more nonlinearities, more interactions, more curvy bits, right? And real life is full of curvy bits, right? Real life does not look like this. But we don't want them to be more curvy than necessary, or more interacting than necessary. So therefore, let's use lots of parameters and then penalize complexity. Okay, so one way to penalize complexity is, as I kind of suggested before, is let's sum up the value of your parameters. Now that doesn't quite work because some parameters are positive and some are negative, right? So what if we sum up the square of the parameters, right? And that's actually a really good idea. Right? Let's actually create a model, and in the loss function we're going to add the sum of the square of the parameters. Now here's the problem with that though. Maybe that number is way too big, and it's so big that the best loss is to set all of the parameters to 0. Now that would be no good, right? So actually we want to make sure that doesn't happen. So therefore, let's not just add the sum of the squares of the parameters to the model, but let's multiply that by some number that we choose. And that number that we choose in FastAI is called WD. Okay? So that's what we're going to do. We're going to take our loss function and we're going to add to it the sum of the squares of the parameters multiplied by some number. WD. What should that number be? Well, generally it should be 0.1. Okay. People with fancy machine learning PhDs are extremely skeptical and dismissive of any claims that a learning rate can be 3e neg 3 most of the time, or a weight decay can be 0.1 most of the time. But here's the thing. We've done a lot of experiments on a lot of data sets, and we've had a lot of trouble finding anywhere a weight decay of 0.1 isn't great. However, we don't make that the default. We actually make the default 0.01. Why? Because in those rare occasions where you have too much weight decay, no matter how much you train, it just never quite fits well enough. Whereas if you have too little weight decay, you can still train well. You'll just start to overfit, so you just have to stop a little bit early. So we've been a little bit conservative with our defaults, but my suggestion to you is this. Now that you know that every learner has a WD argument, and I should mention, you won't always see it in this list, right? Because there's this concept of KW args in Python, which is basically parameters that are going to get passed up the chain to the next thing that we call. And so basically all of the learners will call eventually this constructor, and this constructor has a WD, right? So this is just one of those things that you can either look in the docs or you now know it. Anytime you're constructing a learner from pretty much any kind of function in FastAI, you can pass WD, okay? And so passing 0.1 instead of the default 0.01 will often help. Okay, so give it a go. So what's really going on here? It would be helpful, I think, to go back to lesson 2 SGD, because everything we're doing for the rest of today really is based on this, right? And this is where we created some data and then we added a loss function, MSE, and then we created a function called update, which calculated our predictions. That's our matrix multiply. This is just a one layer, so there's no ReLU. We calculated our loss using that mean squared error. We calculated the gradients using loss.backward. We then subtracted in place the learning rate times the gradients, and that is gradient descent. So if you haven't reviewed lesson 2 SGD, please do, because this is our starting point. So if you don't get this, then none of this is going to make sense. If you're watching the video, maybe pause now, go back, rewatch this part of lesson 2, make sure you get it. Remember, a.sub underscore is basically the same as a minus equals, because a.sub is subtract, and everything in PyTorch, if you add an underscore to it, means do it in place. So this is updating our a parameters, which started out as minus 0.11. We just arbitrarily picked those numbers, and it gradually makes them better. Right? So let's write that down. So we are trying to calculate the parameters. I'm going to call them weights because this is just more common. In kind of epoch t or time t, and they're going to be equal to whatever the weights were in the previous epoch minus our learning rate multiplied by, it's the derivative of our loss function with respect to our weights at time t minus 1. Okay, so that's what this is doing. Okay, and we don't have to calculate the derivative because it's boring and because computers do it for us fast, and then they store it here for us, so we're good to go. Okay, so make sure you're exceptionally comfortable with either that equation or that line of code, because they're the same thing. Where do we go from here? All right. So what's that? What's our loss? Our loss is some function of our independent variables, x, and our weights, right? And in our case, we're using mean squared error, for example, and it's between our predictions and our actuals, right? So where does x and w come in? Well, our predictions come from running some model, we'll call it m, on those predictions, and that model contains some weights, right? So that's what our loss function might be. And this might be all kinds of other loss functions. We'll see some more today. And so that's what ends up creating a.grad over here. So we're going to do something else. We're going to add weight decay, some number, which in our case is 0.1, times the sum of weights squared. Okay? So let's do that. And let's make it interesting by not using synthetic data, but let's use some real data. And we're going to use MNIST, the hand-drawn digits, right? But we're going to do this as a standard, fully connected net, not as a convolutional net, because we haven't learnt the details of how to really create one of those from scratch. So in this case, there's actually deeplearning.net provides MNIST as a Python pickle file. In other words, it's a file that Python can just open up And it'll give you NumPy arrays straight away, and they're flat NumPy arrays. We don't have to do anything to them. So go grab that. And it's a gzipped file, so you can actually just gzip.open it directly. And then you can pickle.load it directly. And again, encoding equals Latin 1 because, yeah, you know. And then we can just put that, that'll give us the training, the validation, and the test set. I don't care about the test set. So generally in Python, if there's like something you don't care about, you tend to use this special variable called underscore. There's no reason you have to. It's just kind of, people know you mean I don't care about this, right? So there's our training X and Y and our valid X and Y. Now this actually comes in as you can see, if I print the shape, 50,000 rows by 784 columns. But those 784 columns are actually 28 by 28 pixel pictures. So if I reshape one of them into a 28 by 28 pixel picture and plot it, right, then you can see it's the number 5. Okay, so that's our data. We've seen MNIST before in its kind of pre-reshaped version. Here it is in its flattened version. So I'm going to be using it in its flattened version, okay? Currently they are NumPy arrays. I need them to be tensors, so I can just map torch.tensor across all of them, and so now they're tensors. Okay. I may as well create a variable with the number of things I have, which we normally call n, and remember we normally have a thing called, we tend to use c to mean the number of activations we need. Well actually, sorry, this is not going to be activations, sorry, this is going to be number of columns. That's not a great name for it, sorry. Okay, so there we are. And then the y, not surprisingly, the minimum value is 0 and the maximum value is 9 because that's the actual number we're trying to predict. Great. So in lesson 2 SGD, we created a data where we actually added a column of 1s on so that we didn't have to worry about bias. We're not going to do that. We're going to have PyTorch do that kind of implicitly for us. We had to write our own MSV function. We're not going to do that. We had to write our own little matrix multiplication thing. We're not going to do that. We're going to have PyTorch do all this stuff for us now. Okay? And what's more, and really important, we're going to do mini batches. Right? Because this is a big enough data set, we probably don't want to do it all at once. So if you want to do mini batches, so we're not going to use too much FastAI stuff here. PyTorch has something called tensor dataset that basically grabs any kind of tensor, two tensors, and creates a dataset. Remember, a dataset is something where if you index into it, you get back an X value and a Y value, just one of them. Okay. So it kind of looks a lot like a list of X, Y tuples. Once you have a data set, then you can use a little bit of convenience by calling databunch.create. And what's that going to do is it's going to create data loaders for you. A data loader is something which you don't say, I want the first thing or the fifth thing. You just say, I want the next thing. And it will give you a batch, a mini batch of whatever size you asked for. And specifically, it'll give you the X and the Y of a mini batch. So if I just grab the next of the iterator, this is just standard Python, if you haven't used iterators in Python before. Here's my training data loader that databunch.create creates for you. And you can check that, as you would expect, the X is 64 by 784, because there's 784 pixels flattened out, 64 in a mini batch. And the Y is just 64 numbers. There are things we're trying to predict. So, if you look at the source code for databunch.create, you'll see there's not much there, right? So feel free to do so. We just make sure that your training set gets shuffled, randomly shuffled for you. We make sure that the data is put on the GPU for you. Just a couple of little convenience things like that. But don't let it be magic. If it feels magic, check out the source code to make sure you see what's going on. Okay. So rather than do this y hat equals x at a thing, we're going to create an nn.module, right? If you want to create an nn.module that does something different to what's already out there, you have to subclass it, right? So subclassing is very, very, very normal in PyTorch. So if you're not comfortable with subclassing stuff in Python, go read a couple of tutorials to make sure you are. Main thing is you have to override the constructor done to init and make sure that you call the superclasses constructor, because nn.modules superclasses constructor is going to like set it all up to be a proper nn.module for you. So if you're trying to create your own PyTorch subclass and things don't work, it's almost certainly because you forgot this line of code. All right, so the only thing we want to add is we want to create an attribute in our class which contains a linear layer, an nn.linear module. What is an nn.linear module? It's something which does that, but actually it doesn't only do that, it actually is x at a plus b. So in other words, we don't have to add the column of ones. Okay, that's all it does. Okay, so if you want to play around, why don't you try and create your own nn.linear class? You could create something called myLinear, and it'll take you, you know, depending on your PyTorch background, an hour or two. And then you'll feel like, okay, we don't want any of this to be magic. And you know all of the things necessary to create this now. So, you know, these are the kind of things that you should be doing for your assignments this week, is not so much new applications, but try to start writing more of these things from scratch and get them to work. Learn how to debug them, check what's going in and out and so forth. Okay, but we can just use nn.linear, and that's just going to do, so it's going to have a def forward in it that goes a at x plus b, right? And so then in our forward, how do we calculate the result of this? Well, remember, every nn.module looks like a function. So we pass our x mini batch, so I tend to use xb to mean a batch of x, to self.lin, and that's going to give us back the result of the a at x plus b on this mini batch. So this is a logistic regression model. A logistic regression model is also known as a neural net with no hidden layers. So it's a one-layer neural net, no nonlinearities. Because we're doing stuff ourselves a little bit, we have to put the weight matrices, the parameters, onto the GPU manually. So just type .CUDA to do that. So here's our model. And as you can see, the nn.module machinery has automatically given us a representation of it. It's automatically stored the .lin thing, and it's telling us what's inside it. So there's a lot of little conveniences that PyTorch does for us. So if you look now at model.lin, you can see, not surprisingly, here it is. Perhaps the most interesting thing to point out is that our model automatically gets a bunch of methods and properties, and perhaps the most interesting one is the one called parameters, which contains all of the yellow squares from our picture, right? It contains our parameters. It contains our weight matrices and bias matrices, in as much as they're different. So if we have a look at p.shape for p and model.parameters, there's something of 10 by 784, and there's something of 10. So what are they? Well, 10 by 784, okay, so that's the thing that's going to take in 784 dimensional input and spit out a 10-dimensional output, because that's handy, because our input is 784 dimensional, and we need something that's going to give us a probability of 10 numbers. After that happens, we've got 10 activations, which we then want to add the bias to. So there we go, here's a vector of length 10. So you can see why this model we've created has exactly the stuff that we need to do our AX plus B. So let's grab a learning rate. We're going to come back to this loss function in a moment, but we can't use we can't really use MSE for this, right? Because we're not trying to say how close are you. Did you predict 3 and actually it was 4? Gosh, you were really close. It's like, no, 3 is just as far away from 4 as 0 is away from 4 when you're trying to predict what number did somebody draw. So we're not going to use MSE. We're going to use cross-entropy loss, which we'll look at in a moment. And here's our update function. I copied it from lesson 2 SGD. But now we're calling our model, rather than going a at x, we're calling our model as if it was a function to get y hat. And we're calling our loss func, rather than calling MSE, to get our loss. And then this is all the same as before, except rather than going through each parameter and going parameter dot sub underscore learning rate times gradient, we loop through the parameters. Okay? Because very nicely for us, PyTorch will automatically create this list of the parameters of anything that we created in our dunder init. And look, I've added something else. I've got this thing called W2. I go through each P in model.parameters and I add to W2 the sum of squareds. So W2 now contains my sum of squareds weights. And then I multiply it by some number, which I set to 1a neg 5. So now I just implemented weight decay. Okay, so when people talk about weight decay, it's not an amazing, magic, complex thing containing thousands of lines of CUDA, C++ code. It's those 2 lines of Python. That's weight decay. This is not a simplified version that's just enough for now. This is weight decay. That's it. Okay, and so here's the thing. There's a really interesting kind of dual way of thinking about weight decay. One is that we're adding the sum of squareds weights. And that seems like a very sound thing to do, and it is. And well, let's go ahead and run this. So here I've just got a list comprehension that's going through my data loader. So the data loader gives you back one mini batch and for the whole thing, giving you X, Y each time. I'm going to call update for each. Each one returns loss. Now, PyTorch tensors, since I did it all on the GPU, that's sitting in the GPU, and it's like got all this stuff attached to it to calculate gradients. It's going to use up a lot of memory. So if you call .item on a scalar tensor, it turns it into an actual normal Python number. So this is just means I'm returning back normal Python numbers. And then I can plot them, and yeah, there you go. My loss function is going down. And you know, it's really nice to try this stuff to see it behaves as you expect. Like we thought this is what would happen. As we get closer and closer to the answer, it bounces around more and more, right? Because we're kind of close to where we should be. It's kind of getting flat, probably flatter in weight space, so we're kind of jumping further. And so you can see why we would probably want to be reducing our learning rate as we go. Learning rate annealing. Okay, now, here's the thing. That is only interesting for training a neural net because it appears here. Because we take the gradient of it. That's the thing that actually updates the weights, right? So actually the only thing interesting about WD times sum of W squared is its gradient. So we don't do a lot of math here, but I think we can handle that. The gradient of this whole thing, if you remember back to your high school math, is equal to the gradient of each part taken separately and then add them together. So let's just take the gradient of that, right? Because we already know the gradient of this is just whatever we had before, right? So what's the gradient of WD times the sum of W squared, right? Let's remove the sum and pretend there's just one parameter. It doesn't change the generality of it. So the gradient of WD times W squared. So what's the gradient of that with respect to W? It's just 2 WD times W. Right? And so remember, this is our constant, which in our case was like, well, in that little loop it was 1e neg 5. Okay? And that's our weights. And like, we could replace WD with like 2WD without loss of generality, so let's throw away the 2. So in other words, all weight decay does is it subtracts some constant times the weights every time we do a batch. So that's why it's called weight decay, right? When it's in this form, where we add the square to the loss function, that's called L2 regularization. When it's in this form, where we subtract WD times weights from the gradients, that's called weight decay. And they are kind of mathematically identical. For everything we've seen so far, in fact, they are mathematically identical. Right? And we'll see in a moment a place where they're not, where things get interesting. Okay, so this is just a really important tool you now have in your toolbox. You can make giant neural networks, right, and still avoid overfitting by adding more weight decay. Okay? Or you could use really small data sets with moderately large-sized models and avoid overfitting with weight decay. It's not magic, right? Like, you might still find you don't have enough data, in which case, like, you get to the point where you're not overfitting by adding lots of weight decay and it's just not training very well. That can happen, right? But at least this is something that you can now play around with. Just to kind of go on here, now that we've got this update function, we could replace this MNIST logistic with MNIST neural network and build a neural network from scratch. Right, now we just need 2 linear layers, right? And the first one, we could use a weight matrix of size 50, and so we then need to make sure that the second linear layer has an input of size 50, so it matches. The final layer has to have an output of size 10, because that's the number of classes we're predicting. And so now our forward just goes, do a linear layer, calculate ReLU, do a second linear layer, and now we've actually created a neural net from scratch. I mean, we didn't write it in linear, but you can write it yourself, or you could like do the matrices directly, you know how to. So again, you know, if we go model.CUDA, and then we can calculate losses with the exact same update function, there it goes, right? So this is why this kind of idea of neural nets is so easy, right? Once you have something that can do gradient descent, right, then you can try different models. And then you can start to add more PyTorch stuff. So like, rather than doing all this stuff yourself, why not just go opt equals optim dot something. So the something we've done so far is SGD. And so now you're saying to PyTorch, I want you to take these parameters and optimize them using SGD. And so this now, rather than saying for P in parameters, P minus equals LR times P dot grad, you just say opt.step. It's the same thing. Okay, it's just less code, right? But, and it does the same thing. But the reason it's kind of particularly interesting is that now you can replace SGD with Atom, for example, and you can even add things like weight decay, right? Because like, there's more stuff that's kind of in these things for you, right? So that's why we tend to use, you know, optim.blah. So behind the scenes, this is actually what we do in FastAI. So if I go optim.sgd, okay, so there's that, right? And so that's just that picture. But if we change to a different optimizer, so look what happened. It diverged, right? We've seen a great picture of that from one of our students who showed what divergence looks like. This is what it looks like when you try to train something. So let's use, we're using a different optimizer, so we need a different learning rate. And you can't just continue training, because by the time it's diverged, the weights are like really, really big and really, really small. They're not going to come back. So start again. Okay, there's a better learning rate. But look at this. We're down underneath 0.5 by about epoch 200, whereas before, I'm not even sure we ever got to quite that level. So what's going on? What's Atom? Let me show you. And we're going to do gradient descent in Excel, because why wouldn't you? Okay, so here is some randomly generated data. Okay, some X's and some Y's. Well, they're randomly generated X's, and the Y's are all calculated by doing AX plus B, where A is 2 and B is 30. Okay, so this is some data that we're going to try and match. And here is SGD. And so we're going to do it with SGD. Now, in our lesson 2 SGD notebook, we did the whole data set at once as a batch. In the notebook we just looked at, we did mini batches. In this spreadsheet, we're going to do online gradient descent, which means every single row of data is a batch. So it's kind of batch size of 1. Okay. So as per usual, we're going to start by picking an intercept and slope kind of arbitrarily. So I'm just going to pick them at 1. Doesn't really matter. So here I've copied over the data. This is my x and y. And so my intercept and slope, as I said, is 1. Right? I'm just literally referring back to this cell here. So my prediction for this particular intercept and slope would be 14 times 1 plus 1, which is 15. And so there's my error, means there's my sum of squareds. Well, not even a sum at this point. It's the squared error. Okay? So now I need to calculate the gradient so that I can update. There's 2 ways you can calculate the gradient. One is analytically. And so, you can just look them up on Wolfram Alpha or whatever. So there's the gradients if you write it out by hand or look it up. Or you can do something called finite differencing, because remember, gradients just how far you move in, how far the outcome moves divided by how far your change was for really small changes. So let's just make a really small change. So here we've taken our intercept and added 0.01 to it, right? And then calculated our loss. And you can see that our loss went down a little bit, right? And we added 0.01 here. So our derivative is that difference divided by that 0.01. Okay? And that's called finite differencing. You can always do derivatives with finite differencing. It's slow. We don't do it in practice, but it's nice for just checking stuff out. So we can do the same thing for our A term, add 0.01 to that, take the difference and divide by 0.01. Or, as I say, we can calculate it directly using the actual derivative analytical. And you can see that, that and that are, as you'd expect, very similar. And that and that are very similar. So gradient descent then just says, let's take our current value of that weight and subtract the learning rate times the derivative. There it is, right? And so now we can copy that intercept and that slope to the next row and do it again. And do it lots of times. And at the end, we've done 1 epoch. So at the end of that epoch, we could say, oh, great. So this is our slope. So let's copy that over to where it says slope. And this is our intercept. So I'll copy it to where it says intercept. And now it's done another epoch. Okay? So that's kind of boring, copying and pasting. So I created a very sophisticated macro which copies and pastes for you. And so I just recorded it basically. And so and then I created a very sophisticated for loop that goes through and does it 5 times. And I attached that to the run button. So if I press run, it'll go ahead and do it 5 times and just keep track of the error each time. Okay, so that is SGD. And as you can see, it is just infuriatingly slow. Like particularly the intercept is meant to be 30. And we're still only up to 1.57 and it's just going so slowly. So let's speed it up. So the first thing we can do to speed it up is to use something called momentum, right? So here's the exact same spreadsheet as the last worksheet. I've removed the finite differencing version of the derivatives because they're not that useful, just the analytical ones here. And here's the thing where I take the derivative and I'm going to update by the derivative. But what I do, it's kind of more interesting to look at this one, is I take the derivative and I multiply it by 0.1. And what I do is I look at the previous update and I multiply that by 0.9 and I add the two together. So in other words, the update that I do is not just based on the derivative, but 1/10 of it is the derivative, and 90% of it is just the same direction I went last time. And this is called momentum, right? What it means is, remember how we kind of thought about what might happen if you're trying to find the minimum of this, and you were here and your learning rate was too small, right? And you just keep doing the same steps. Or if you keep doing the same steps, then if you also add in the step you took last time, then your steps are going to get bigger and bigger, aren't they? Okay, until eventually they go too far. But now, of course, your gradient's pointing the other direction to where your momentum's pointing, so you might just take a little step over here, and then you'll start going small steps, bigger steps, small steps, bigger steps, like that, right? So that's kind of what momentum does. Or if you're kind of going too far, like this, which is also slow, right, then the average of your last few steps is actually somewhere kind of between the two, isn't it? Right? So this is a really common idea, right? It's like when you have something that says kind of my, what is it in this case? It's like my step at time t equals some number. People often use alpha because, like I say, you've got to love these Greek letters. Some number times the actual thing I want to do, right? So in this case, it's like the gradient, right? Plus 1 minus alpha times whatever you had last time, st minus 1. This thing here is called an exponentially weighted moving average. And the reason why is that if you think about it, these 1 minus alphas are going to multiply. So st minus 2 is in here with a kind of a 1 minus alpha squared. And st minus 3 is in there with a 1 minus alpha cubed. So in other words, this ends up being the actual thing I want plus a weighted average of the last few time periods where the most recent ones are exponentially higher weighted. Okay? And this is going to keep popping up again and again. Right? So that's what momentum is. It says I want to go based on the current gradient plus the exponentially weighted moving average of my last few steps. So that's useful. That's called SGD with momentum. And we can do it by changing this here to saying SGD momentum. And momentum 0.9 is really common. It's, I don't know, it's so common it's always 0.9 just about for basic stuff. So that's how you do SGD with momentum. And again, it's not, I didn't show you some simplified version, I showed you the version that is SGD. Okay, that's you, again, you can write your own, try it out. That would be a great assignment, would be to take lesson 2 SGD and add momentum to it. Or even the new notebook we've got for MNIST, get rid of the optim dot and write your own update function with momentum. Then there's a cool thing called RMS-prop. One of the really cool things about RMS-prop is that Geoffrey Hinton created it, a famous neural net guy. Everybody uses it. It's like really popular. It's really common. The correct citation for RMS-prop is the Coursera online free MOOC. That's where he first mentioned RMS-prop. So I love this thing that, like, you know, cool new things appear in MOOCs, not a paper. So RMS-prop is very similar to momentum, but this time we have an exponentially weighted moving average, not of the gradient updates, but of f8 squared. That's the gradient squared. So what the gradient squared times 0.1 plus the previous value times 0.9. So it's this is an exponentially weighted moving average of the gradient squared. So what's this number going to mean? Well, if my gradient's really small and consistently really small, this will be a small number. If my gradient is highly volatile, it's going to be a big number, or if it's just really big all the time, it'll be a big number. And why is that interesting? Because when we do our update this time, we say weight minus learning rate times gradient divided by the square root of this. So in other words, if our gradient's consistently very small and not volatile, let's take bigger jumps. And that's kind of what we want, right? When we watched how the intercept moved so damn slowly, but it's like, obviously you need to just go faster. So if I now run this, after just 5 epochs, this is already up to 3, right? Whereas with the basic version, after 5 epochs, it's still at 1.27. And remember, we have to get to 30. So the obvious thing to do, and by obvious I mean only a couple of years ago did anybody actually figure this out, is do both, right? So, and that's called ATOM. So ATOM is simply keep track of the exponentially weighted moving average of the gradient squared, and also keep track of the exponentially weighted moving average of my steps, right? And both divide by the exponentially weighted moving average of the squared terms and take 0.9 of a step in the same direction as last time. So it's momentum and RMS prop. That's called ATOM. And look at this. Okay, 5 steps, we're at 25. Okay, so these optimizers, people call them dynamic learning rates. A lot of people have the misunderstanding that you don't have to set a learning rate. Of course you do, right? It's just like trying to identify parameters that need to move faster, or are consistently going in the same direction. It doesn't mean you don't need learning rates. We still have a learning rate. Okay, and in fact, if I run this again, currently my my error. No, just do it again. So we're trying to get to 30,2. So if I run it again, it's getting better, but eventually, now it's just moving around the same place, right? So you can see what's happened is the learning rate's too high. So we could just go in here and drop it down and run it some more. Getting pretty close now, right? So you can see how you still need learning rate annealing even with ATOM. Okay, so that spreadsheet's fun to play around with. I do have a Google Sheets version of basic SGD that actually works and the macros work and everything. Google Sheets is so awful and I went so insane making that work, I gave up on making the other ones work. So I'll share a link to the Google Sheets version. Oh my God. They do have a macro language, but it's just ridiculous. So anyway, if somebody feels like fighting it to actually get all the other ones to work, they will work. It's just annoying. So maybe somebody can get this working on Google Sheets too. Okay, so that's weight decay and ATOM. And ATOM is amazingly fast. And let's go back to this one. But we don't tend to use optim.whatever and create the optimizer ourselves and all that stuff, because instead we tend to use Learner. But Learner's just doing those things for you, right? Again, there's no magic, right? So if you create a Learner, you say, here's my data bunch, here's my PyTorch nn.module instance, here's my loss function, and here are my metrics. Remember, the metrics are just stuff to print out. That's it, right? Then you just get a few nice things like learn.lrfind starts working and it starts recording this. And you can say fit 1 cycle instead of just fit. But like these things really help a lot. Like by using the learning rate finder, I found a good learning rate. And then like look at this, my loss here, 0.13. Here I wasn't getting much beneath 0.5. Right? So these tweaks make huge differences, not tiny differences. And this is still just one epoch. Now, what does fit 1 cycle do? What does it really do? This is what it really does. Right? And we've seen this chart on the left before. Just to remind you, this is plotting the learning rate per batch. Right? Remember, Adam has a learning rate. And we use Adam by default, or minor variation, which we might try to talk about. So the learning rate starts really low and it increases about half the time, and then it decreases about half the time. Because at the very start, we don't know where we are, right? So we're in some part of function space that's just bumpy as all hell, right? So if you start jumping around, those bumps have big gradients and it'll throw you into crazy parts of the space, right? So start slow. And then you'll gradually move into parts of the weight space that, you know, they're kind of sensible. And as you get to the points where they're sensible, you can increase the learning rate, you know, because the gradients are actually in the direction you want to go. Right? And then, as we've discussed a few times, as you get close to the final answer, you need to anneal your learning rate to hone in on it. But here's the interesting thing. On the left is the momentum plot. And actually, every time our learning rate is small, our momentum is high. Why is that? Because if you do have a small learning rate, but you keep going in the same direction, you may as well go faster. Right? But if you're jumping really far, don't like jump really far because it's going to throw you off, right? And then as you get to the end again, you're fine-tuning in, but actually if you keep going in the same direction again and again, go faster, right? So this combination is called 1 cycle, and it's just this amazing, like it's a simple thing, but it's astonishing. Like this can help you get what's called superconvergence that can let you train 10 times faster. And this is just last year's paper. And some of you may have seen the interview with Leslie Smith that I did last week. Amazing guy, incredibly humble. And also, I should say, somebody who is doing groundbreaking research well into his 60s. And all of these things are inspiring. I'll show you something else interesting. When you plot the losses with FastAI, it doesn't look like that. It looks like that. Why is that? Because FastAI calculates the exponentially weighted moving average of the losses for you. Right? So this concept of exponentially weighted stuff, it's just really handy. And I use it all the time. And one of the things is to make it easier to read these charts. Okay? It does mean that these charts from FastAI might be kind of an epoch or two, a batch or two behind where they should be. You know, there's that slight downside when you use an exponentially weighted moving average is you've got a little bit of history in there as well, but it can make it much easier to see what's going on. So, we're now at a point coming to the end of this Colab and tabular section where we're going to try to understand all of the code in our tabular model. So remember the tabular model uses this data set called adult, which is trying to predict who's going to make more money. It's a classification problem. And we've got a number of categorical variables and a number of continuous variables. So the first thing we realize is we actually don't know how to predict a categorical variable yet, because so far we did some hand waving around the fact that our loss function was nn.crossentropyLoss. What is that? Let's find out. And of course, we're going to find out by looking at Microsoft Excel. So, cross-entropy loss is just another loss function. We already know one loss function, which is mean squared error, y hat minus y squared. Okay, so that's not a good loss function for us, because in our case we have, like for MNIST, 10 possible digits, and we have 10 activations, each with a probability of that digit. Okay. So we need something where predicting the right thing correctly and confidently should have very little loss. Predicting the wrong thing confidently should have a lot of loss. So that's what we want. Okay, so here's an example. Here is cat versus dog, one hot encoded. Okay? And here are my two activations for each one from some model that I built. Probability cat, probability dog. This one's not very confident of anything. This one's very confident of it being a cat and it's right. This one's very confident of being a cat and it's wrong. So we want a loss that for this one should be a moderate loss, because not predicting anything confidently is not really what we want. So here's a 0.3. This thing's predicting the correct thing very confidently, so 0.01. This thing's predicting the wrong thing very confidently, so 1. So how do we do that? This is the cross-entropy loss, and it is equal to whether it's a cat multiplied by log of the probability of cat, or this is actually an activation, so I should say. So it's multiplied by the log of the cat activation, negative that, minus, is it a dog, times the log of the dog activation. And that's it. Okay, so in other words, it's the sum of all of your one-hot encoded variables times all of your activations. So interestingly, these ones here are exactly the same numbers as these ones here, but I've written it differently. I've written it with an if function, because it's exactly because the zeros don't actually add anything, right? So actually it's exactly the same as saying, if it's a cat, then take the log of cattiness, and if it's a dog, so otherwise, take the log of 1 minus cattiness, in other words, the log of dogginess. So the sum of the one hot encoded times the activations is the same as an if function, which if you think about it, it's actually, because this is just a matrix multiply, this is, we now know from our embedding discussion, that's the same as an index lookup. So you can also, to do cross entropy, you can also just look up the log of the activation for the correct answer. Now that's only going to work if these rows add up to 1. And this is one reason that you can get screwy cross entropy numbers, is that's why I said you press the wrong button. If they don't add up to 1, you've got a trouble. So how do you make sure that they add up to 1? You make sure they add up to 1 by using the correct activation function in your last layer, and the correct activation function to use for this is softmax. Softmax is an activation function where all of the activations add up to 1, all of the activations are greater than 0, and all of the activations are less than 1. So that's what we want, right? That's what we need. How do you do that? Well, let's say we were predicting one of 5 things: cat, dog, plane, fish, building. And these were the numbers that came out of our neural net for one set of predictions. Well, what if I did e to the power of that? So that's one step in the right direction, because e to the power of something is always bigger than 0. So there's a bunch of numbers that are always bigger than 0. Here's the sum of those numbers. Here is e to the number divided by the sum of e to the number. Now this number is always less than 1, right? Because all of the things were positive, so you can't possibly have one of the pieces be bigger than 100% of its sum. Okay? And all of those things must add up to 1, right? Because each one of them was just that percentage of the total. So that's it. So this thing, softmax, is equal to e to the activation divided by the sum of e to the activations. And that's called softmax. And so when we're doing single label multi-class classification, you generally want softmax as your activation function, and you generally want cross entropy as your loss. And because these things go together in such friendly ways, PyTorch will do them both for you. Right? So you might have noticed that in this MNIST example, I never added a softmax here. And that's because if you ask for cross-entropy loss, it actually does the softmax inside the loss function. So it's not really just cross-entropy loss, it's actually softmax then cross-entropy loss. So you've probably noticed this, but sometimes your predictions from your models will come out looking more like this, pretty big numbers with negatives in, rather than this, numbers between 0 and 1 that add up to 1. The reason would be that PyTorch, it's a PyTorch model that doesn't have a softmax in because we're using cross-entropy loss, and so you might have to do the softmax for it. FastAI is getting increasingly good at knowing when this is happening. Generally, if you're using a loss function that we recognize, when you get the predictions, we will try to add the softmax in there for you. But particularly if you're using a custom loss function that might call an n.crossentropy loss behind the scenes or something like that, you might find yourself with this situation. We only have 3 minutes left, but I'm going to point something out to you, which is that next week, when we finish off tabular, which we'll do in like the first 10 minutes, this is forward in tabular. And it basically goes through a bunch of embeddings, right? It's going to call each one of those embeddings E, and you can use it like a function, of course. So it's going to pass in each categorical variable to each embedding. It's going to concatenate them together into a single matrix. It's going to then call a bunch of layers, which are basically a bunch of linear layers. And then it's going to do our sigmoid trick. And then there's only 2 new things we need to learn. One is dropout, and the other is, the ncont, batch norm. And these are 2 additional regularization strategies, right? They're basically, batch norm does more than just regularization, but amongst other things it does regularization. And the basic ways you regularize your model are weight decay, batch norm, and dropout. Okay, and then you can also avoid overfitting using something called data augmentation. So batch norm and dropout we're going to touch on at the start of next week. And we're also going to look at data augmentation, and then we're also going to look at what convolutions are, and we're going to learn some new computer vision architectures and some new computer vision applications. But basically, we're very nearly there. You already know how the entirety of collab.py, fastai.collab works. You know why it's there and what it does, and you're very close to knowing what the entirety of tabular model does. And this tabular model is actually the one that if you run it on Rossmann, you'll get the same answer that I showed you in that paper. You'll get that second place result. In fact, even a little bit better. I'll show you next week, if I remember, how I actually ran some additional experiments where I figured out some minor tweaks that can do even slightly better than that. So yeah, we'll see you next week. Thanks very much and enjoy the smoke outside.